I will give you introduction of lunar geology and show you some basic features that you can find commonly on Moon. Before I start, I will give you, I would like to say something about origin of the Moon. And there are several theories related to the formation of the Moon. But most common one includes, sorry, my animation is a bit forward. So the most common one includes when the Mars-sized body Theia hit the molten Earth. This was at the time when the planet was still protoplanet and it's a molten, and then it left the debris around this molten body or protoplanet, and this debris then collected into a single satellite, which we see as a moon now. So when early moon was formed, it was covered with the magma ocean, and this magma ocean actually crystallized over the time. So when 80% of the magma ocean was crystallized with the heavy minerals, including olivine and pyroxene, then the lighter minerals start getting crystallized and form the proto or early crust, which was rich with feldspathic minerals. And the residual of the magma ocean was enriched with potassium, rare earth elements, and phosphorus, which is known as the creep. And this layer was sandwiched between heavy mineral and lighter minerals. And the time period when this happened, or when the whole process occurred, it varies from model to model, and it's still under discussion. So the solidification could be occurred in a 10 million year to 220 million year. So stratigraphy, Carolyn had covered in detail how you set the stratigraphic on a planetary body where you don't have a fauna and flora. And for specifically Moon, I will introduce it again, that the stratigraphic system of Moon are named after basins and craters. The earliest one is named after Nectaris Basin here. It's one of the older basins on Moon. And during the Nectarian period, the dominated process on the surface of Moon was the basin formation, and there might have some volcanism, but it's so difficult to find out about it. And the next stratigraphic period is named after Imbrium Basin, and mainly because ejecta from the Imbrium Basin covered or affected a lot of other surfaces or other geological units on Moon. So this was also the period where a lot of the cratering were happening. However, in the late Imbrian period was dominated by volcanism, and we see the formation of mare at this age. Or it was it was the main process, but still cratering was still occurring during this time. The earlier stratigraphic periods are named after two craters, Rathathenius and Copernicus. And the difference between these two is Rathathenius are the older one, which do not show the ray patterns. However, the Copernican are the younger one, which shows the ejected material and the fresh ray pattern. So these were the two craters that these periods were named after and divided into. So, if I journalize the geological processes that occur on Moon, we see the four main geological processes that occurred. Okay, the cooling of magma ocean that created the earlier crust, and then later there was a lot of volcanism, and cratering occurred like throughout the history of Moon. And then there is kind of tectonic. It's a single plate tectonic, which means that the tectonic features are dependent on regional stresses, and this was also discussed by us yesterday in detail. So What are highlands? So highlands, as name described, these are higher elevation region. If you look at the moon at the naked eye, this is the lighter material you see on the moon. And this is these are the older. It means they are really reworked earlier crustal material. They are heavily cratered, and because I say that this is where the earlier crustal material could be present, or we could find there, it's enriched in this lighter mineral that formed this earlier crust, like energetic compositional. However, highland is not a single geological unit. It consists of several different geological units. It has ejecta material from Nectarian and Imbrium age um, basins and ejecta that we see we can find some remnants of them. We also see Imbrium age basin ejecta. For example, Faramaro Formation is a ejecta material from Imbrium basin. And then we have some like a plain material which consists of ejecta deposit of the different craters. So so we do recognize different geological units in highland, you could say, on the base of roughness and crater density. Volcanism is also would say second most common process on moon. And when we again look at the moon with the naked eye, we see these dark spots on the moon. These are Mare units. They are volcanics, and we say they are like low albedo units. They fill the depressions, they fill the basins and low elevation area. And in spectral data, we identify them with a higher iron content. So talking about spectral data, it will be covered in detail later, and it was covered earlier before in this week. So yeah, we use spectral data to identify different Mare units. And here we have example from Singer et al. 2000, where he used Galileo spectral data to identify boundaries between different volcanic flows on the differentiating on base of different spectral properties, mean different compositional properties. Later, they measured ages of this volcanic deposit and come up with a map of all volcanic units or whole Mare units on the moon, along with the history of volcanic evolution. So now I will just show some few common features you can observe in the spectral data. Here we see there's some volcanic, some Mare flow fronts. These are, we have to be a bit lucky to see them, because we always see them in a low sun angles, or I would say high incidence angle images. So here's an example of Apollo images where we can see some of them. But yeah, you can see that it's different from wrinkle ridges. They're more low-lying flatter than wrinkle ridges, which I will also explain later. Then we can also see some volcanic tubes or lava tubes. Sometimes we find a rimless, ejecta-less crater in the Mare area, which is indication of there is a volcanic tube present there. And normally we see them as a sinus rills in the Mare deposits. We also can identify pyroclastic deposits on moon. Like Earth, they're also the fine grain material, but the deposit depends on the volume. So we can find a very small deposit, here is the one in Schrodinger Basin, and we also find them in a larger volume where they covered several other geological units or overlay on several other geological units. We also can identify by high-density silica-rich volcanic eruption in form of volcanic domes. And these are, you also can easily identify them in Oceanus Porcelarum region, for example. And as I mentioned before, wrinkle ridges are tectonic feature based on mare, restrictive mare. You commonly find them in mare because it formed due to the collapse due to this contractional when a lot of mare deposits or volcanic deposits are accumulated and fall on their own with their own weight, and it forms the first fault. So we hardly find any volcanic feature isolated from each other. They are always you can identify them in clusters. For example, in this image, we can see a volcanic tube in mare unit and dome and wrinkle ridges. We see a pyroclastic vent as well as pyroclastic deposit here. And then cratering. As I say, cratering is the most common process on Moon, and it occurs throughout the lunar history. This was covered in detail by Carolyn yesterday, so I just give a small recap. So here we see that how the different age craters are differentiated on base of the morphology. For example, Preambrium or Nectarian craters, we can they do have a really degraded crater rims and hardly identifiable ejecta. In Imbrium craters, we can identify rims, but we don't. We can also see the extent. We can identify extent of the ejecta material. It's also very highly degraded. Reptilian craters are the sharp rim craters. They do have an ejecta material, but they do not have the rays, as I described it before. Unlike Copernican craters, which has the sharp rims, ejecta material, and rays. So here is a image of the Tycho crater from Lunar Orbiter 4. And which was taken in 1967. And here is the high resolution image of the Tycho crater from ALARO-NAC data. And first thing is that when we look at these images for first time, we cannot identify, because we see them in the map view, we don't identify what is depression and what is dome in these images. And the trick for doing that is to look for incidence angle, look where the sunlight is coming from. Here in this image, in the map view, we see that the sun is more shining on this side of the central peak and the wall, which is similar like that. Is shining to the central peak and the wall, and the shadows are formed on a different, on the opposite side. And I will use similar view for schematic diagram to explain how we see these images. So Carolyn also explained it yesterday in detail. We can identify the central peak, which is the cluster, which is the chaotic cluster of several thrust faults. We can identify a crater wall, which consists of several normal faults. We can see hummocky floors here, which is brecciated. Brecciated material consists of big boulders, and the smooth parts that are covered in there are kind of melt. And to identify ejecta material, we can identify the parts which are near crater rims. They are hummockier. They consist of, again, bigger boulders and bigger material. Then the next one afterward comes the ejecta material that is radially, that shows a radial pattern. that is indicating back to the crater of origin. And afterward is a part of the ejecta material that consists of the secondary crater and chains that were produced by this initial crater. Going back to this image, we can see again, here is a central peak we can see in this view. Then there is the homocular floor here, which is brecciated floor. Then we have a crater walls. We can also identify them here. And then we have a smooth areas in between, which are like impact melt pools. So here this image is a high incidence image where the sun is, you can consider it on the top of the image, so we don't have shadows. And here we can see the near crater rim, there are more and bigger ejecta material. Here also these bigger dots are boulder material. They are more homocular and rougher material. And as we go apart from this one, we can see this is this radial pattern of ejecta moving back to the crater. So this crater is on the rim of another crater. That's why the ejecta is moving down from here. So you can identify impact melt as a pools, but sometimes you can identify impact that melts on the slopes, and there you can see these lobate patterns on impact melt where it shows this their flowing direction. You can identify on the base of the difference albedo, but as well as on the finer grain morphology. And you can identify it when it cools down. It shows this quenching properties where you find the single boulder or cluster of the boulders which just cool down and break at its own place. Tectonics, this was covered very well by Oz yesterday, but here I just give you a brief introduction again. So as I say, that on Moon we have a regional, the tectonics depends on the regional stresses. And here we see the compressional wrinkle ridges. Here we have extensional features like grabens, and here again we have a compressional feature like a scarp. So grabens are extensional features that consist of two normal faults, and it shows, you can find them on highlands, and you can find them as well as on Mare units. And wrinkle ridges are the compressional feature which we find on Mare units, where and you could see them in the segmented sections, and the scarps are more smoother thrust faults, which are mostly found on highlands. So now I give it to Sasha, who will explain you how you map all these geological features.
So hopefully you can see my screen now.
Yes, and we can hear you too.
Great. Then I take it away and introduce myself. Shortly, I'm Sasha Mikolajewski, a second-year PhD student at Harald Hiesinger's working group. And there I'm researching pyroclastic deposits on the Moon, and also planning and investigating landing sites and planning rover traverses. So I will give you a brief summary of how to create geological maps for the Moon, and give some examples from my own projects. So let's get started. The introduction I give is, first, when you prepare a mapping project, you'll start with setting up the directory with different folders for the data sets, and it's much easier if you have all the stuff in one place. Here I've also added a folder for literature for the mapping area available. And the next step in your mapping project is that you choose, as we heard in multiple talks over the week, that it's very important that you choose an appropriate projection angle for your map, as we've heard that if the central meridian is in the center of your projected map, then the craters in the center of the area are more appropriate and get not distorted than if you move away from your central meridian. And it's also important in mapping that you add different data sets to your directory. Like I said, I have here Clementine image, as we have heard before, Kaguya mineral maps, and also different instruments like gravity data from Grail, and different parameters like rock abundance, Christiansen feature, to differentiate the minerals we found on the moon. And last but not least, you need to choose the software for digital mapping. I mostly work with ArcGIS, but today we will map with QGIS. There are many others you can use for digital mapping. So, most important takeaway message you need to remember is save many and save often. Save when you made some edits to your files, also when you add new data. And the most important thing when you work on mapping projects is that you have a backup of your files and also of your project located on a different location. That could be another hard drive or stored in the cloud. And also important is that you always use the same version of your software. For example, in ArcGIS, it's no problem if you load an older version into the newer ArcGIS because it's upwards compatible, but not downwards compatible. So let's get started. First, it is important that you know your mapping area. Here, for example, shown on the right-hand side is an image from the lunar far side. Marked with an orange box is Mare Moscoviense, one of the areas I mapped as for my master's thesis. And we will go through Moscoviense, and I will show you some examples on how to create a map and also how to plan it, lander and rover traverse. So first, you need some literature for your mapping area, and also what is also helpful, a WAC or Kaguya image for getting a brief overview of the mapping area. And then you collect the data you need for your mapping project. Like I work with WAC, NAC, and Kaguya mosaics for image and albedo differences. If I want to characterize minerals, I mainly use Clementine and Kaguya mineral maps. And as I mentioned before, I also use additional data sets like Diviner and Grail. Grail, for example, is gravity data, so that you can identify objects hidden under the subsurface. And when it comes to identifying features, you start with drawing outlines to mark where you have an approximate or an appropriate contact. So let's dive more into Mare Moscoviense. It is located on the lunar far side. There's several literature available of Mare Moscoviense. Here are some examples of people who worked at Moscoviense. And this gives you a brief overview of the study area. And I used here a WAC mosaic as a base map, and you can see in this mosaic the inner crater rim, the outer crater rim, and Moscoviense is a complex crater with presumably an oblique impact with the impactor coming from the northeast to the flying towards the southwest, hitting around here. And you can also identify around here the outermost rim of the impact basin. So with that, it comes to data collection. So we use the WAC mosaic together albedo information, the DEM for topographic information. Here you can see the rims that I showed you before, the inner one, second one, and the outermost. And as you heard in the talk before, we use also spectral information to differentiate different features found inside the basin. And when it comes to planning a landed mission or a rover traverse, or for asteroids, EVAs, we use high resolution neck images. On the image on the left-hand side, you can see the difference between the resolution difference between the WAC and the neck image. We can then also use high resolution elevation models as shown in the central image, and from this high resolution elevation model we can derive a slope map to plan rover traverses and astronaut activities. When it comes to identifying features, there are several mapping standards, like paper from Greeley and Paxton about planetary mapping, and also the stuff from the USGS shown here on the right-hand side, the FGDC Planetary Geological Features document, where for any given feature you found on a planetary surface, you have the appropriate symbol. For example, as mentioned before, for drawing an accurate contact, you have this solid line, and for approximate contact, you have this dashed line. So when it comes to identifying features, there are several principles available for that. They refer to Steno from 1669. So the first principle is, as we heard in a talk on, I think it was Monday, about superposition. You can imagine it like the layers of a cake, where you have the oldest layer at the bottom and stacking up younger ones on top. And also cross-cutting relationships are used for identifying the relations between units. Here, for example, in this image, this larger crater is the oldest one because the rim of this large crater is cross-cutted by this smaller one here. And when you have samples available, you can also look for inclusions where you have a large host rock in which a younger dike or other material is ingested. And another principle is the original, that all layers are deposited horizontally. It relates also to the cake example I gave before, so that when all the layers are laying down, they are all like this. You have the oldest one at the bottom and the youngest one on top. And the last principle is lateral continuity. For example, in this image, the layers on top of this side should also be the same than the layers on this side. And when it comes down to craters, you mark the young crater first, then the older one. For example, in this image, the youngest crater is this one, crater A. You can also see a bit of the ejecta blanket of this crater, and that the crater also modified the rim of the oldest crater in this image. Next crater in the series would be B, who modified the oldest crater in the image. And the oldest crater then in this series is the large one, crater C. And then you drew your outlines for your units. As I've shown here, this black line refers to crater with a large diameter. And in the talk from Wajiha, we heard also about identifying craters. So I go briefly through that again. Just as a quick reminder, we have this pre-Imbrian craters, which are relatively worn down, no ejecta is visible, the rim is not as sharp as compared to other craters. Then we have the a bit younger Imbrian craters where sometimes the ejecta is visible, the rim is a bit sharper compared to the pre-Imbrian craters. Then we have the younger Eratosthenian craters where you can also trace the ejecta a bit, the rim is sharper compared to the Imbrian craters. Then we have the youngest crater in our series, the Copernican crater. In the project you will work on, we work with a crater Copernicus. Here's one example of another Copernican crater. You can see ray material, this bright stuff here, and also here, rays from this small crater which impacted here. And you can also trace the ejecta blanket. Other crater features we find on planetary surfaces are crater chains and also secondary craters that tend to be more clustered. And as Wajiha mentioned before, there are also other structures you can identify, like wrinkle ridges, which tend to be a bit more topographically higher compared to the surrounding material. You have rills of different origin that tend to be a bit topographic lower. Then you have also melt patches and, as we heard before, volcanic domes. So when it comes to identifying features, rule of thumb for referring to ejecta blanket is that the ejecta blanket equals as 1 times the diameter of the crater, depending on the planetary surface we are, the surface composition, and also the composition of the impactor and the angle on which the impactor impacted on the surface. So when you mark your features, you can do it in 2 ways, and don't do it the wrong way shown here. In this series, the red crater is the oldest, the greenish one is the youngest, is the second oldest, and these 2 yellow ones are the youngest. So to represent that, the green one overlies the red one, and the 2 yellow ones modified the rim of the green one. This down here is how you don't do that, because that's wrong. Younger unit overlay older ones, and for example, you can remember this one here, or also if you have a lava flow, the lava flow should flow into the older unit rather than appearing to have been cut off from the older unit. And as we heard in the talk before by Francesca, when it comes to identifying features, we also use spectral data. We saw the Clementine color ratio composite, where blue is related to high titanium basalts, this reddish hue is related to mature highland material, and this orange hue up here is related to low titanium basalts. We can also use the Kaguya mineral map. For example, I used here the Kaguya iron map, where you see that here's an area with a relatively high iron content, and here is an area which is poor in iron. And with all information we can start mapping. So I'll start with drawing an outline of a first unit related to the spectral data I gathered, difference in albedo, and also a difference in how the surface looks. If you look, this surface left and right from this central part are less cratered. This one is a bit higher in albedo, this one is darker, and this one here is heavily cratered. So then we add some morphologic features like this floor fractured craters, and at the last step we add different spectral features and also different albedo units and morphologic units, and with that we can get this final map. This is my presumably map for the Moskowiense area. And this map I used for a landing site analysis, which I will show you now. So when it comes down to landing site analysis, first you start with choosing an area of interest. For this area of interest, then look what scientific goals you can achieve in this area. Then if you have a good NAC coverage, because if we have seen it before, you need use NAC images to plan your rover traverses, look for hazards for your lander and your rover. And plus for your area of interest would be if you have resources available you can explore. Also a good plus is if the area is good accessible. For Moskowiense, you have a bit of a downside because it lies on the far side of the moon. There you need a relay satellite to communicate with Earth, which makes the mission a bit more costly. And also you need to reconsider the lander and rover safety. And when you have done all that, you can start with planning your traverse. And for that, it is good to have a geological map as a backup. And lucky me, I have that for this area. So I show you two examples for a landing site study I've carried out. One is located here in the north, refers to the orange star. The other one is a bit more south, referring to this purple star. So let's have a detailed look of both sides. One is located on an Eratosthenian Mare unit, the other one on an Imbrian Mare unit. The land we planned here with an activity of around 15 kilometers around a central landing area. And then we looked at the NAC DEM. You can see both areas are relatively smooth, no great height differences. From this NAC DEM, we derive a slope map. It's a bit noisy, but no great color differences. So the areas are relatively smooth, which is good for landing there and also good for planning a traverse. And last but not least, we look at the rock abundance of the area. And here you can see that on this unit, it would be safer to land a bit more to the north. Here we have only a larger rock concentration from this fresh impact crater located here. So to sum this shortly up, at the landing site orange site, we can sample one Mare unit. The area is relatively flat, and there are a few large craters compared to the surrounding area. The cons are that we can only sample one geological unit. The rock abundance is only low in the northern part of the area, and it is located on the lunar far side. So for Purple Star, we could sample 2 additional units. We have a low rock abundance. The area is relatively flat, and there are also relatively few large craters compared to the surrounding area, and we can land. And the downside is also that it's located on the far side. So another area I investigated, and there I added some mobility. So here I plan a small rover traverse with a landing ellipse of around 100 kilometers in the Rima-Bode, a landing ellipse of around 100 meters at the Rima-Bode area. Rima-Bode, the area is located south of the Mare Imbrium. So let's have a closer look here. Here is the 100-meter landing ellipse and a small rover traverse of 1.5 kilometers. On the way, we could sample different larger boulders and rocks. And at our final stop with spectroscopy, we can sample from afar with camera instruments this brighter stuff here. And we can also have a look down in this vent located here. So you can see that we have here a depression, and here's this it's also a depression which could be associated to fissure volcanism like the one we see on Hawaii or Iceland. So when it comes to traverse planning, we wanted to assure that the track is relatively smooth and flat. So the height difference is roughly 20 meters from landing point to start point. We assure that we have the rover always have contact with the lander, and here on the slope maps you see that we are relatively safe to go there because the angle is not larger than 7 degrees on our track here. So to sum things up, mapping a surface is easy to learn and hard to master. You always have to keep your stratigraphy in mind. It is best for you to not rely on only one data set alone. You may have to make consistent decisions during your map generation. So if you have to say, I think this unit is older, then you can go for it and you have to argue why you think it is older. And when it comes to select a landing site, you want to achieve multiple goals, like you want to achieve the scientific goals for the landing site should be set. You check if you have net coverage available or other high resolution data. And the research exploration is a plus for making the site more appealing for funding. And also good is for funding that you keep in mind the accessibility of the site to reduce costs. And a plus would also be lander and rover safety is improved with flat terrain and few large craters in range. And with that, I'm at the end of my talk and open for questions.